So I'm going to begin solving some of the problems on the midterm review. Since this is a course in cryptography, the most important problems are the first three where we actually do cryptography as opposed to the underlying algebra and number theory that you need for the codes. So the first is the easiest. We have a Caesar code with a shift of 7 letters. So A, B, C, D, E, F, G, H, I, J, K, L, and so forth. If you shift A to the right by 7 letters, 1, 2, 3, 4, 5, 6, 7. So A becomes an H. B becomes I, and so forth. C becomes J. Let's see, this is first, second, third, fourth. This is the 5th letter. 6, 7, 8, 9, 10. That's the 10th. I is, for example, 6, 7, 8, 9. This is the 9th letter. So the 16th letter is A, B, C, D, E, F, G, H, I, J, K, L, M. This is 11, 12, 13, 14, 15, 16. So if you shift E 7 letters to the right, that's the 12th letter, which is L. If you shift I 7 letters to the right, that becomes a P. So for example, if you take the first name Alice, so this is my plain text, and you encrypt it, you get Alice. A is H, L is, let's see, 12, goes to the 19th letter, Q, R, S. L goes to S, H, S, I goes to P, C goes to J, and E goes to L. So that's the ciphertext. So if you wanted to transmit the name Alice using a Caesar code with shift 7, if I did my counting correctly, what you actually send is HSPJL. And to decipher it, you just take each letter and on the alphabet circle, move each letter 7 letters to the left, and you will recover Alice. And that's all it is. Now, problem 2, using Diffie-Hellman to transfer a key or to establish a secret key between Alice and Bob. Alice chooses the secret number for her, A equal to 4. And Bob chooses the secret number for him of B equal to 5. And what is in the public domain is the prime P equal to 97 and the primitive root G equal to 10. So Alice is going to calculate the number capital A, which is G to the 4th, which is 10 to the 4th, mod 97. And she's going to send that to Bob. And Bob is going to compute G to his secret number, which is 5. So that's 10 to the 5th. Reduce that mod 97. So Alice sends A to Bob, and Bob sends B to Alice. And how do they get their secret key? So the secret key, which they both share, is Alice takes B and raises it to her secret number A. And Bob takes Alice's A and raises it to his secret number B and reduces this mod 97. So we have to do a little bit of arithmetic here. And it really is a little bit. I mean, you can do it if you like by hand, or you can use the calculator, or you can use a computer. If I take the least positive residue of, there's a congruence class, what is 10 to the 4th congruent to mod 97? So I have to take 10 to the 4th, if I'm doing it by hand, divide it by 97, or a computer can do it for me. And the computer tells me that this is 9. So A is 9, and capital A. And Bob's secret number, or Bob's public number, he takes G equal to 10 and raises it to the 5th power, and he gets the number 90. So the secret key, Alice gets the number B from Bob, capital B, raises it to the power A. So this is 90 raised to A equal to 4, and reduces that mod 97. Let's see. And what is 90 to the 4th power? Mod 97, that's 73. And Bob should get the same result. He takes Alice's public number, capital A, raises it to his secret number, 5. So we're calculating nine to the 5th, mod 97. And this is also 90, which is also 73. So the answer to this problem is 97. So what is known in the public domain, everybody knows, even the eavesdroppers, is we're taking the prime 97, the primitive root 10. And now Alice and Bob want to establish a number that they both know and no one else does. It's their secret key. So Alice chooses her secret number, little y equal to 4, calculates G to the 4th, which is 10 to the 4th, G to the A, which is 10 to the 4th, mod 97, and gets 9. So she sends 9 to Bob. Bob takes G, which is 10, and raises it to his secret number, 5, reduces it mod 97, and gets 90. And so everyone knows the number capital A that Alice sends to Bob, and everyone knows the number 90 that Bob sends to Alice, but only they can figure out from those numbers how to calculate something which gives them the same number, 73. So this is an example of the Diffie-Hellman key exchange method. This is really very important. Problem 3 is an example of the Elgamal public key crypto system. Public key crypto system. So in this case, they don't want to, Alice and Bob don't want to somehow create a number they both share. Bob actually has a message he wants to send to Alice, and he wants to be able to send it so Alice can decode it, decipher, or decrypt it, but no one else can. So again, we start with a prime number. In this case, let's take a small prime, p equal to 13, and the primitive root, G equal to 2. So these are public knowledge. Everybody in the universe knows for this crypto system, the prime P is 13, the primitive root mod 13 is G equal 2. So Alice chooses her secret number, little a, and she's going to choose the number 7. And then she calculates capital A, which is G to the A mod P. P is 13 in this case. G is 2. 2 to the 7th mod 13. What is 2 to the 7th mod 13? No, actually, we don't even need a calculator for this. What is 2 to the 7th? 2 to the 7th is 128. And mod 13, you divide 128 by 13, you get a remainder of 11. So A is equal to 11. And Alice sends this number A equal to 11 to Bob. So Bob knows this number A that Alice sent to him. Now, Bob has a message he wants to send to Alice. The message has to be something between 1 and P. So let's say that Bob's message that he wants to send to Alice is, and a message is everything is translated into a number. So the message is 9. So Alice wants to send Alice the message 9 in such a way that no one can intercept and know what his message is. So Bob chooses a random element, a random number, K. Let's say he picks K equal to 3. And he computes two numbers, C1 and C2. So C1 is G to the K mod P, which is what? G is 2, K is 3, mod 13. 2 cubed is 8. So C1 is 8. And C2 is the message M times A to the K. Capital A is the number that Alice sent him. M is 9, so this is 9 times 11 cubed. And we want to reduce that mod 13. Again, these are pretty small numbers. You could do it by hand, or you can do it really any way you like, calculator, computer, whatever. This is 9 times 11 cubed. And we want to know what is that mod 13. And when I calculated, I get 6. So Bob takes this pair C1, C2, which is equal to the pair 8, 6, and he sends it back to Alice. So Alice gets the pair So Alice receives the pair 8, 6 from Bob. Again, it's important to keep in mind what's actually being transmitted. So Alice sends Bob the number 11. Bob sends the pair 8, 6 back to Alice. And how does Alice decipher the plain text? So what Alice does is calculate the following. So what Alice does is calculate. She takes the first number, C1, raises it to the power A, her secret number, takes the inverse of that, and multiplies it by C2, and reduces this mod to prime 13. So what is this? The message is C1 to the A. C1 is the number 8. Alice's secret number, little a, was 7. And we want the inverse of that, mod 13, times C2, which is 6. So we want this mod 13. So we have to calculate this number. Calculating this to the -1 can be done in a very simple way. You have to recall Fermat's little theorem, which in this case says that if you take any number a relatively prime to 13, like 8, 8 to the 12th power is congruent to 1 mod 13. So 8 to the 12th power, so this is 8 to the 7th inverse. That's 8 to the minus 7th is the same as 1 times 8 to the minus 7th, and 1 is 8 to the 12th times 8 to the minus 7th. This is 8 to the 5th mod 13. And 8 to the 5th, let's make it easy. I can do it on a calculator. 8 is 2 cubed to the 5th. So that's 2 to the 15th, which is 2 to the 12th times 2 cubed. 2 to the 12th is 1 because 2 is relatively prime to 13. So this is just 2 cubed, or 8 mod 13. So the message is 8 times 6, which is 48. And what is 48 mod 13? Well, 3 times 13 is 39, so this is congruent to 9 mod 13. So lo and behold, through the magic of the Elgamal crypto system, Alice figures out that the message that Bob is sending her is message m equal to 9, which is exactly correct. So this is the crypto system. This is really very, 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 very important to know. And definitely has to be on the YouTube. Problem 4 is another problem using the Elgamal crypto system. So again, we start with P equal to 13, G equal 2, and we're not going to know how everyone gets their numbers, just what's going on. How do you decrypt the message? So we're told that Alice sends Bob, and she has her secret key A equal to 4. That's all Alice knows. So what she sends to Bob is the number A, which is congruent to 2 to the 4th mod 13, which is 16 mod 13. So she sends Bob the number A equal 3. And Bob chooses his random element K, comes up with a pair of numbers C1, C2, and he sends them to Alice. And that's the numbers 11 and 2. So you're Alice, you know your secret number 4, and Bob has sent you this pair 11, 2. And Alice must decrypt, decipher, decode 11, 2 to get the message M. And what does Alice do? The message is C1 to the A inverse C2 mod P. That's what Alice has to calculate. So C1 is 11. A is equal to 4. So Alice has to calculate 11 to the 4th power inverse times C2 times 2 mod 13. So again, you can calculate this in a variety of different ways. Again, using the fact that 11 to the 4th to the minus 1 is 11 to the minus 4th power, which is congruent to, I multiply this by 11 to the 20th, 11 to the 12th, because 11 to the 12th is congruent to 1 mod 13, so you can always by Fermat's little theorem. So you can always multiply by 1, which is 11 to the 12th. So 11 to the 12th times 11 to the minus 4th. So you want to calculate 11 to the 8th. What's 11 to the 8th? Let me just do it by hand. 11 is congruent to minus 2 mod 13. So this is minus 2 to the 8th mod 13. It's an even power. So that's the same as 2 to the 8th mod 13. 2 to the 8th is 2 to the 4th times 2 to the 4th. That's equal to 16 times 16 mod 13. 16 is 3 mod 13. So that's congruent to 3 times 3, or 9 mod 13. So this is the decryption using Elgamal. Okay. That is cryptography. The next problems on the review are problems on the number theory and algebra that underlie all of our cryptography methods. Problem 5 is to factor the first 4 digits of your ID number. And problem 6 is to factor some other numbers. Let me just do a couple. This is just trial and error and experience. 12 is, I don't know, 3 times 4. 4 is 2 times 2 times 3. So the prime factorization is 2 times 2 times 3, or 2 squared times 3. 123, I can divide that by 3, I get 41. 41, if you try to divide it by factors, you see you can't, that's the prime, that's it. What about 1234? No. I have no idea how to factor it a priori, but I do know it's even, so I can divide it by 2. I get 2 times 617. Let's see, what can I say about 617? I can't divide it by 2. It's not divisible by 2, or 3 or 5. Very easy to check. What about 7? I don't know. Just have to do try on it. 7 into 617. 8 sevens are 56. 57. No, it doesn't go. 11. 11 doesn't go. It really is just a matter of trying to see if it has any factors. It turns out it doesn't. So 41 is a prime. So that's the factorization. 617 is also a prime. So this is the factorization. It's just a matter of having some time, some paper and pencil, and an eraser, and trying to work it out. We have the same problem in problem 7. We start with the number 4,116, and we want to see how often the primes 2, 3, 5, and 7 divide this number. So again, the best thing perhaps is to try to factor it. Let's see, this is certainly even. Let's see, is it divisible by 4? 4, 1, 1, 6, this goes in once. This goes in twice. 9 times. So this is 4, or 2 squared, times 1029. Let's see, is 1029, it's not divisible by 2, certainly not divisible by 5. Is it divisible by 3? 2, 3, 9, 12, 4, 12, 9, 3. So this is 2 squared times 3 times 343. Turns out if I try to divide this by 7, I can. If I keep dividing by 7, I think this is exactly 7 cubed. So 4,116, when you write it as a product of prime powers, is exactly this. So the highest power of 2 that divides this number, 2 to the second power is 2. The highest power of 3 that divides this number is the first power. The highest power of 5 that divides this number is the 0th power, because there's no power of 5 here. If you like, it's 5 to the 0, it's the 0th power. That means 5 doesn't divide the number. And the highest power of 7 that divides 4,116 is 3. The 7 cubes divide that number. So that's what it is. Problem number 8 is to look at the prime p equal to 11 and try to find a primitive root. So normally you start with the smallest numbers you can, like 2. So what are the powers of 2 mod 11? 2 to the first power is 2 mod 11. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16, which is 5 mod 11. 2 to the fifth is 2 times 2 to the fourth is 10, which is the same as minus 1 mod 11. So 2 to the sixth is 2 times 2 to the fifth, that's minus 2, which is 9 mod 11. 2 to the seventh is 2 times 9 is 18, is 7 mod 11. 2 to the eighth is 2 times 7 is 14, which is 3 mod 11. 2 to the ninth is 2 times 3 is 6 mod 11. And 2 to the 10th is 12, which is 1 mod 11. So the smallest power of 2, which is congruent to 1 mod 11, is the 10th power. So G equal 2 is a primitive root. And I just calculated 2 to all powers k, for k from 1 to 10. So that's that. Problem 9 is to show that 927, is to show that 3 is not a primitive root mod 13. So again, the only way to do that is to start calculating the powers of 3. 3 to the first power is congruent to 3 mod 13. 3 squared is 9. 3 cubed is 27, which mod 13, oh, it's 1. Wow. So 3 cubed is 1 mod 13. So 3 is not a primitive root. What about 2? Right. That is for an element is a primitive root mod 13 if the smallest power of the number, which is congruent to 1 mod 13, is the 12th power. So if we're going to prove 2 is a primitive root mod 13, I have to calculate the powers of 2. That's just a calculation. 2 to the first power is 2 mod 13. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16, which is the same as 3 mod 13. 2 to the fifth is 2 times 2 to the fourth is 6. 2 to the sixth is 2 times 6 is 12, which is minus 1 mod 13, not plus 1. 2 to the 7th is 2 times 2 to the 6th is minus 2 or 11. 2 to the 8th is minus 4. This is all mod 13. So minus 4 is the same as 9. 2 to the 9th is going to be, for example, 18, which is the same as 5. 2 to the 10th is 10 mod 13. 2 to the 20th, 2 to the 11th will be 2 times 10, which is 20, which is 7 mod 13. And 2 to the 12th is 2 times 7 is 14, is 1 mod 13. So the smallest power of 2 that's congruent to 1 mod 13 is the 12th power. So 2 is a primitive root. And the logarithm of 11 to base 2 mod 13, what power of 2 gives you 11? The 7th power. So that's the discrete logarithm. Problem 10 is very similar. So let me jump to problem 11. Problem 11 says to use fast factoring to compute (3 to the 50). This might be a horrible calculation. But in fast factoring, what you do is you take the exponent, write 50 as a sum of powers of 2. So 50 is 32 plus 18. 32 is 2 to the 5th. 18 is 16 plus 2. So 50 is 2 to the 5th plus 2 to the 4th plus 2 to the 1st power. So 3 to the 50th will be 3 to the 2 plus 2 to the 4th plus 2 to the 5th. That's 3 squared, 3 times 2 to the 4th, 3 times 2 to the 5th. Let's see. So 3 squared is 9. 3 to the 4th is 3 to the 2 squared. That's 3 to the 2nd power squared. That's 9 squared. 3 to the 8th is 3 to the 4th squared, which is, this is 3 to the 4th, 9 to the 4th. 3 to the 16th is 3 to the 8th squared, which is 9 to the 8th. And 3 to the 32nd, 2 to the 5th, is 3 to the 16th squared, which is 9 to the 16th. So what we get is that this is equal to 9 times 9 to the 8th times 9 to the 16th power. In any case, what you don't have to do is multiply 3 by itself 15 times. This is just a number that's too big to write down. I'm just going to leave it at that. Really, the point of doing this fast factoring is when you're dealing with moduli. So let me do number 12. We want to compute 7 to the 21st power mod 31. So again, we start by writing 21 as a sum of powers of 2. 21 is 1 plus 4 plus 16. That's 2 to the 0 plus 2 squared plus 2 to the 4th. So 7 to the 21 is 7 to the 1 plus 4 plus 16. It's 7 times 7 to the 4th, that's 7 squared squared, plus 7 to the times 7 to the 16th power, which is 7 times 2 to the 4th. But we want to compute this mod 31. So 7 to the first power is 7 mod 31. 7 squared is 49. 49 is 18 mod 31. 7 to the 4th power is 7 squared squared. That's 18 squared. What is 18 squared? I believe it's 324. And if you take 324 and you divide it by 31, you get 10 something. So let's see, this is 324, which is 310 plus 14. So 7 to the 4th is congruent to 14 mod 31. 7 to the 8th is 7 to the 4th squared, is congruent to 14 squared. 14 squared, I believe, is 196. You divide 196 by 31. 31 goes into 196, probably 6 times, and leaves a remainder of 10 mod 31. And 7 to the 16th is 7 to the 8th squared, would be congruent to 100. 3 times 31 is congruent to 7 mod 31. So 7 to the 21st power is congruent to 7 times 7 to the 4th, which is 14, times 7 to the 16th, which is also 7. So what we get is, if you multiply this, this is really 2 times 7 cubed, which is 2 times 343, which is 927. Is that right? That's not right. 2 times 343 is 686. And if you take 686 and divide it by 13, you get, what do you get? $686 divided by 31. I think you get a remainder of 4 mod 31. Let me just check. You divide 31 into 686, this goes twice. 62, 86, that goes twice. 66, that goes twice. That leaves a remainder of 4. So the answer is 721 is congruent to 4 mod 31. So that's using the fast factoring algorithm to compute this. Okay. Problem 13 is the Euclidean algorithm applied to the numbers A equal 387 and B equal to 51. So if you take, 387. If you take 387 and divide it by 51, you get a quotient, I think, of 7. So 7 times 51 is 357. And that seems to leave a remainder of 30. 51 divided by 30 is 1, and leaves a remainder of 21. 30 divided by 21, the quotient of 1, and leaves a remainder of 9. 21 divided by 9 has a quotient of 2, and a remainder of 3, and 9 divided by 3 has a remainder of 0. So the greatest common divisor of 387 and 51 seems to be equal to 3. And to work backwards, to write 3 as a linear combination with integer coefficients of 51 and 387, we work backwards like this. 3 is equal to 21 minus 9 times 2, which is 21 minus, and 9 is 30 minus 21 times 2. So this is 21 times 3 minus 30 times 2. And 21 is 50 minus 30. So it's 50 minus 30 times 3 minus 30 times 2, which is 50 times 3 minus 30 times 5. And oops, should be 51. 51 times 3. And that's 51 times 3 minus, and 30 is 387 minus 51 times 7 times 5. So I have 35 plus 3, I have 51 times 38 minus 387 times 5, and that's supposed to equal 3. Since I always make arithmetic mistakes, I always like to check. So what is 51 times 38? $1938. What is 387 times 5? It's 1935. If I subtract, I get 3. So this is 100% correct. Now, the remaining problems are things which you literally look up in your book and learn. Definitions. What does the word encryption mean? What does the word decryption mean? Plain text, ciphertext, a Caesar cipher, a frequency table for a substitution cipher. This is historically very important. The fast powering algorithm, which we just used. What does the fundamental theorem of arithmetic say? Euclidean algorithm, Fermat's little theorem, public key cryptosystem. What is a one-way trapdoor function? An example is the discrete logarithm. The difference between a symmetric and asymmetric cipher. This is really, you should really write out these answers. I mean, you learn something by writing it down very often. So to explain in your own words the Diffie-Hellman key exchange in the Elgamal cryptosystem, these are very important. Problem 18, the two separate parts. If you're a math student, you're supposed to learn how to prove stuff. So you might try to prove that every positive integer can be represented uniquely as a sum of powers of 2. And if you're a computer science student, you're supposed to know computer programming. So you might try to write a program that computes the binary representation of your integer and test it by using your student ID number. And that, in fact, is the entire review for the midterm.